NASA has finally unveiled the eagerly awaited images of the interstellar comet 3I Atlas, putting an end to weeks of speculation that arose due to the lack of updates amid the US government shutdown. The newly processed information verifies what scientists had anticipated from the beginning. 3I Atlas behaves just like a natural comet, even though it comes from outside our solar system. Numerous spacecraft have now provided new perspectives, allowing researchers a more detailed view of its activity and structure. In this video, we will delve into what these images disclose and their significance concerning this interstellar traveler. Let's dive in. DISCOV-RYV3I Atlas comet was first discovered in early July by the Atlas Survey Telescope. The object quickly attracted attention because its trajectory was clearly hyperbolic, indicating that it isn't gravitationally bound to the Sun and is merely passing through our solar system on a one-time journey. This acknowledgement marked it as only the third confirmed interstellar object ever detected, following Oumuamua and 2I. Shortly after the discovery, the comet passed behind the Sun, entering its most active phase and reaching under ordinary circumstances, this would have been followed by a continuous stream of scientific updates. However, with NASA's communications halted during the government shutdown, the public found itself without key information just when the comet was exhibiting the most activity, leading to rampant speculation. Once operations resumed, NASA released a full array of observations to clarify the situation, directly addressing social media rumors. The newly published imagery is varied, with NASA's Mars Reconnaissance Orbiter offering some of the closest views as the comet crossed near Mars, capturing detailed images with its high-rise camera. MAVEN contributed ultraviolet data instrumental in identifying the gases being released as the comet heated up. Solar observation missions like Stereo documented wide-angle images of its tails and dust structures. Even spacecraft on different missions, such as Lucy and Psyche, managed to capture distant views of the comet. What distinguishes this dataset is the comprehensive coverage. Instead of sporadic observations from a singular telescope, scientists possess a continuous multi-mission record incorporating various wavelengths, viewing angles, and distances. These images track the comet's activity during its peak solar engagement, illustrating how its coma and tails transformed as it got closer to and then receded from the Sun. As the comet moves further away and gradually dims, this collection of images has solidified its status as the definitive record of its journey, providing astronomers with key data for long-term analysis, enabling them to reconstruct not just the object's actions, but also the physical processes affecting it during its transient stay in the inner solar system. Scientific importance and XORIS-3I Atlas's significance lies not in its unusual behavior, but rather in its familiar actions, despite its interstellar origin. This consistency enables researchers to draw parallels in the formation of icy bodies around different stars. Early spectroscopic measurements indicated a relatively high carbon dioxide to water ratio, an anomaly for many comets within our solar system, but not impossible. The recent ultraviolet data will help determine if this characteristic is primordial or a consequence of prolonged exposure to radiation in interstellar space. Cosmic radiation is critical in shaping these types of objects. Comets traveling for eons through the Milky Way experience incessant bombardment from energetic particles that alter surface chemicals, possibly darkening, hardening, or chemically rearranging outer layers. Understanding how these changes manifest in 3I Atlas could shed light not only on its composition, but also on the environmental alterations it has undergone during its extensive journey. Another area of scientific interest focuses on the structure of its coma and tails. Multiple images indicated asymmetrical tails and dust patterns, influenced by both solar radiation and the comet's exceptionally high speed. Since interstellar comets often travel much faster than typical bodies within our solar system, the released dust behaves uniquely. Gas jets erupting from the surface might curve or stretch unexpectedly under the effects of high velocity, motion, and varying solar angles. By comparing these traits to the behaviors observed in 2I Borisov, researchers may pinpoint which characteristics serve as common identifiers of an interstellar origin. NASA also confronted the surge of online theories, questioning if the object was artificial. These speculations were fueled by the coincidental timing of the shutdown and early images showcasing irregular shapes and unusual brightness levels. Scientists clarified that these features were standard artifacts related to viewing geometry, resolution, and image processing. The newly issued high-resolution images exhibit a classic comet structure, complete with a dusty coma, a luminous core region likely concealing the frozen nucleus, alongside bright tails shaped by solar heating. One of the most compelling questions revolves around the comet's age. Estimations of its velocities, faster than nearby stars orbiting the galactic core, have led researchers to speculate that the comet may have been journeying through interstellar space for billions of years. This suggests that it originated in a star system older than our own, long before the Sun and its planets formed. If this hypothesis holds, 3I Atlas not only hails from a different solar system, but also represents a bygone era in the galaxy's history. This potential transforms the comet from a mere rare visitor into a time capsule. Investigating the gases it releases as it warms offers scientists valuable insights into conditions present in early planetary systems. Were initial icy bodies abundant in carbon dioxide? Did they include varying ratios of organics or metals? Have their surfaces undergone significant alteration due to cosmic radiation? These are crucial questions regarding the diversity of worlds within the Milky Way, and interstellar comets like 3I Atlas present the only feasible means to explore these inquiries. Collectively, the new images and measurements furnish scientists with the most comprehensive data set available for an interstellar comet since born. They enable researchers to test theories regarding comet formation, radiation processing, and the behavior of high-velocity dust, still fundamental for grasping planetary system evolution over galactic timescales. Implications and what's unexplained. Unveiling of the 3I Atlas imagery signifies the commencement of a more in-depth scientific phase. With the comet now dimming, attention will pivot to analyzing its composition, dust structures, and tail dynamics through the amassed dataset. As the observations encompass a variety of wavelengths, scientists can investigate how different ices sublimate, what molecules chiefly constitute the coma, and how dust grains are distributed surrounding the nucleus. Should the comet indeed be as ancient as models indicate, these measurements could unveil significant details about the environments of early star formation. Identifying specific molecules may also assist in determining whether the object originated near a sun-like star or from an entirely different kind of stellar system. By contrasting its chemistry with what is known about solar system comets, researchers may highlight either similarities or stark differences in the formation processes of icy bodies in distant regions of the galaxy. NASA also assured that the comet posed no threat to Earth at a distance exceeding 170 million miles. During its closest approach, it remained far outside any potential impact scenarios. However, the public's reaction underscored a vital point, that rare astronomical events can quickly lead to misunderstandings if communication is inadequate. This likely will affect how announcements and updates regarding future interstellar discoveries are managed. As we progress, telescopes will continue to monitor 3I Atlas 4 as long as it remains observable, although it will progressively fade as it drifts outward. Nevertheless, the scientific exploration is just beginning. The rich dataset obtained during its active phase will support years of studies focused on dust physics, sublimation chemistry, radiation processing, and dynamics of interstellar objects. This event has also reignited interest in future missions aimed at intercepting or swiftly approaching interstellar bodies. Both Oumuamua and 3I Atlas traverse too rapidly for spacecraft to reach them. But there are now proposals for interstellar interceptors that could be launched quickly once a new object is detected. As detection systems improve, these missions might eventually facilitate close-up explorations of interstellar visitors. Ultimately, 3I Atlas serves as a reminder that our solar system is part of a more extensive galactic ecosystem. Occasionally, objects from distant stars come into our vicinity, offering a fleeting yet invaluable perspective on conditions we cannot observe directly. The new images from NASA capture this moment with remarkable detail, providing an extraordinary record of a traveler from another world. Outro the 3I Atlas comet presents a rare interstellar phenomenon, affording a brief glimpse into material that predates our Sun. NASA's latest images elucidate its true nature and offer scientists a robust basis for further investigation. As analysis proceeds, this interstellar guest will aid in deepening our understanding of how remote planetary systems develop and evolve.